So now the thing to keep in mind is that when we look at equilibrium expressions, we can actually solve for a mathematical value. We can plug numbers in for these concentrations and solve for the constant K. If we go back to this original reaction that we had here, this is straight out of the book on page 761 if you want to look at it. If we were to look at this and say when we start the reaction, I have an initial concentration, so we're going to call that I, the initial concentration of 0.0175 molar of both of these things. When I first start, I won't have any of my product. And what we're going to see is as time happens, this reaction begins to change. These reactants are going to react with each other, and they're going to go down. Because of the stoichiometry, them both being a one-to-one relationship, the amount that goes down has to be the same. So this is going to lose 0.0138 molar, as this loses 0.0138 molar. And at the same time that those are losing, this is going to have to be increasing at twice the rate. Again, going back to the kinetics, if this is how fast this one's going away, this one's going to increase twice as fast, 0.0276. So when I get to the very, very end, my equilibrium concentrations, these are not completely gone. Remember that hydrogen and iodine are also being formed as the hydrogen iodide goes in the reverse reaction. So this stuff does not go away completely. In fact, instead, I'll have 0.0037 if I subtract these two values, and 0.0037. But over here, 0 plus 0.00276 is 0.0276 here. So now if we go back to our equilibrium expression that we had written for this equation, we would have the concentration of Hi squared divided by the concentration of H2, also divided by the concentration of I2. And when I do math and I put these together, I'll end up with a final answer of 56. So I kind of skipped a step there. Let's look at what we actually did. We plugged in 0.0276 squared, and we divided that by 0.0037 times 0.0037. So now when we do this mathematics, you will see that that does equal approximately 56. I think we rounded that to two significant figures, but you get the idea. So what we're looking at here is that when we take the actual concentrations that are given to us in the reaction, when they tell us what the concentrations at equilibrium are for the hydrogen iodide and for the reactants, we can solve for a value of K. So let's look at another problem. So when we look at this reaction that we had earlier, the nitrogen, hydrogen, and ammonia, we know that the equilibrium expression K is going to be equal to NH3 squared divided by N2 divided by H2 cubed. So if we knew equilibrium values, we could then figure out the value of K. The other thing that is true is this is just simple algebra, that if I know the value of K and I know these concentrations, two of the three, I can solve for the one that's missing. So here is a way to be able to do these. If they tell you what the value is and they tell you what the concentrations are, it just becomes an algebra. So we know that this reaction, and again, you don't know this, I just know because I happen to look it up in the book, the K for this at a given temperature is going to be 6.3. If K equals 6.3, and I know that the concentration of the ammonia at equilibrium is 0.47 molar, I want to know, oh, I take that, see, I'm messing this up already. It's not what I wanted. I want 6.3 is the concentration of that. I don't know the concentration of the ammonia, but I know that the concentration of the nitrogen when I got to equilibrium was going to be 0.47, and the concentration of hydrogen due to the reaction was 0.93. If this is true, now I can just do algebra to solve for this concentration of X. It just becomes an algebra problem, so when I rearrange and do this problem, I can end up with 2.38 equals X squared. So the idea behind this is when I cube root this value, or not cube root, cube 0.93 times 0.47, and I cross multiply to get it with the same side as 6.3, that isolates this thing by itself. That is going to be X squared. So 2.38 equals X squared. I take the square root of that answer, and my final answer of X, the concentration of the ammonia at equilibrium, is going to be 1.54 molar. So now again, the units on K are usually not given. They're going to be ignored. And when we finally get to the end result, whenever we solve for a concentration, you can almost always assume that the units are going to be molarity. as we go through these problems, there's something else that we need to keep in mind, and that is what this value of K means. So if I'm looking at A plus B forming C and D, there's something to keep in mind here. If K is a value that is greater than 1, if K is greater than 1, what does that mean mathematically? Well, remember that K is products over reactants, right? So mathematically, if this value is going to be greater than 1, then there has to be more product than there is reactant. There's going to be more product in order to make this ratio, P over R, greater than 1. If K is less than 1, then the products are going to be less than the reactants, right? Because algebraically speaking, whatever this value is, if this is less than 1, then the reactants are going to be greater than the products. Because in order to get a ratio where this fraction mathematically is less than 1, the ratio has to be more reactant, less product. So what we say about these is if K is greater than 1, this is called product favored. It means that the reaction wants to go in the forward direction. There is more stuff becoming products than there is products becoming reactants. If K is less than 1, then we say that it is reactant favored. Again, this time the reaction isn't going very much to products. There's not very much product being produced. It's more reactants. So K is less than 1. Now what's going to actually end up happening in most reactions, especially the ones that we say are non-reversible, if a reaction is non-reversible, that means that in order for that to happen, K is going to be much, much larger than 1, in the thousands and tens of thousands. And if it does not react at all, so a reaction that is non-forward, like it doesn't even react, I guess that's the best way of saying it. If we say that there's, quote, not rho, let's try that again. If there is no reaction, then K is going to be much, much less than 1. So what we end up seeing, and we'll talk about this later, probably on Tuesday in class, is that when the K is really, really small, 0.0000013, something like that, then that is a lot of reactant is still left over, and there's not very much product left at all. The product did not get produced. So things like solubility, when we said things like, this substance is insoluble, what's really happening is it's not insoluble. It just means that not very much is dissolving. Most of it is staying as reactant. And so we don't see that reaction going towards products. All right? So the value of K is an important thing. So very, very small Ks stays as reactants. Very, very large Ks goes to products. There's one other thing that we need to talk about on this lesson, and then we'll quit and we'll pick the rest of this up on Tuesday. And that has to do with when we have gases. So normally we're talking about equilibrium being K. You're actually going to see two different versions of K. There's K with a subscript C, and there's K with a subscript P. This little c tells us that this is going to be based on concentration. But the thing about gases is if everything inside my reaction is for all gas reactions, then the P here is going to stand for pressure. Because the volume of the container will be constant, there's multiple gases inside there, and so we're going to look at Kp. There is a mathematical relationship between Kp and Kc, and so what we need to be able to look at is understand the difference between them. For me, in my class, I don't see a difference between writing Kp and Kc and how it works, but what we're going to end up looking at is that Kp is going to be the pressure of some gas. What's the one that, let's use the one we just did where it was ammonia NH3 squared, and this would be, it's going to be regular, the pressure of nitrogen and the pressure of hydrogen cubed. So it's going to be pressure based. And what ends up happening with these is with pressures, we have to bring in the whole idea of R. Remember that whole gas law R thing that we had earlier? Well, for these, we're going to see that the relationship is Kp equals Kc times RT raised to the change in number of moles. RT raised to the change in number of moles. So again, going back to our reaction, I'm running out of room here on this page. If we had N2 plus 3 H2s forming 2 NH3s. In this, we started with 4 moles of reactant, and we ended up with 2 moles of product. So delta N here is a negative 2. So this value would be a negative 2 power. If we know the Kc, which I said earlier was 6.3, times R times T raised to the negative 2 power, we would then get the value of Kp. And those pressures are almost always in atmospheres. The value of R on this is going to be a different value of R. This one is going to be, give me a second. Okay, I was wrong the first time. This R value is going to be our still 821. 0.0821. That is the value of R. T still has to be in Kelvin, and this is a relationship that I could go into a lot of detail of how it's derived, but it's not really that important. But this formula is very important that you know that you understand how to use that. That Kp equals Kc times RT raised to the delta N, where you're looking at the change in number of moles. Final minus initial number of moles in the reaction. So 2 moles ended up here. We started with 4 moles, so it's going to be a negative 2 for that reaction. If it's the same number of moles, so again, if when we did the reaction, if it was like the very, very first one that we did, let's go back over there to, not that page, let's go to this, nope, not that page either. If we went to this, I have 1 mole and 1 mole, so there's 2 moles on this side and 2 moles on this side. These were all gases. I didn't write them down because I got lazy. If there's 2 moles on both sides, in this case, Kc is going to be equal to Kp, because the delta N is 0, and anything raised to the 0 power is 1, so Kp equals Kc for this reaction. We're going to go ahead and stop there. Give me just a second, and I will tell you some problems out of the book that you should be able to work on. Just kidding. We have to talk about Q. Q is called the reaction quotient, which means we can use conditions that are given to us to compare if this reaction is actually at equilibrium or not. So Q is going to be the same thing. It's going to be Q equals the concentration of products divided by the concentration of reactants. But instead, we're going to compare this value. Whatever the conditions are that we are given to here, we're going to compare those conditions to see if we're at equilibrium or not. If it's not at equilibrium, then Q is not going to be equal to K, right? If the products are not the same as the reactants, then Q is not equal to K, and it's not at equilibrium. So what we want to look at here is we're going to take values that they give us, and we're going to plug them into the same expression, the same equilibrium expression of products over reactants, but instead of calling it K, we're going to call it Q. If the value of Q is too big, if Q is larger than K, then what do we have? If we have too much product and not enough reactant, then that's what's going to happen. Okay? We have too much product. We're not at equilibrium. The reaction is going to shift to the left. Okay? If Q is less than K, then I don't have enough reactant. I don't have enough product. The value of this ratio is not big enough. So in this case, we have too little product, and the reaction is going to proceed, or we're going to say that it shifts to the right. Okay? It has to allow that reaction to continue to move to allow those things to happen. Again, you can read through this stuff in the book on those pages that I have written down at the top of this page on Moodle. And here are the problems that I would like you to work on from the into the book. It's page 789. If you can do numbers 1, number 3, number 5, then we're going to skip ahead a little bit to number 9 and to number 11. Okay, if you can do those 5 problems before you come to class on Tuesday, that'll be highly beneficial. We'll talk more about these. We'll do a couple sample problems in class. I will try to give you some more practice problems to do for homework, and we should be ready to move along and continue going. Pass the word to everybody to make sure that they watch this. And again, I appreciate you guys doing this for homework. Hopefully we'll get back caught up with everything we've got going on, and we'll be ready to go and get you guys prepared to take this AP test in May. Have a great weekend, folks, and if not over the weekend, then see you Monday night and see you Tuesday in class.